So straight lines. Straight lines. This is the basic example at the top. Just one example for the whole thing. Vector, and then it's vector, one vector v and one point p, and then what it amounts to, building a line, is that little formula over there. So you add all multiples of v to p. Okay, so at every time when you add a vector to a point, what do you get? You get another point. Okay, so as you can see over there, start with p, and then you have p plus v, p plus 2v, and so on, and that is a very compact way of representing it. Also, don't forget, if you know, algebra is not entirely comfortable yet with vector algebra, then think about motion. So a motion in space, you have, you know, the direction, the velocity, and you know your initial position p, and that way you get the whole thing. Okay, so these are the examples. Once again, if you want to think about the line as a geometric object as such, so then it is like a road. So the difference between what we're looking at, that formula in the middle, and a line as a geometric object is like a difference between a road, and how you drive on that road. Okay, so once again, a line, if you draw a line on the plane, so that's not the same. That's not the same because that particular representation of our line depends specifically on p and v. But not only that, it also indicates in what particular way we are moving through this line. Okay, so the line, everybody can move it different way. You can move faster, slower. You can actually even reverse the direction. I mean, either you're going that way or that way. So there are two possibilities, and then we specify that differently. So why ambiguity? And the ambiguity comes from over here. The difference between the function, the function and its image. This is the image. Okay, so the road is the image of your trip. The trip involves how fast and when. Okay, the road doesn't know that, and but you can, as you can see, what we are concerned with is your trip rather than the road. The road only gives you the whatever is in kind of in stone in that, and so some of the parts are missing, and therefore some of the information about your function is missing. So that is where's that picture that I made of this one. As you can see that the two pictures on the right is one is the graph, and the graph contains all the information about the function, because for every x there is a input. For every t, the input, there is an output, which is a point on the plane. Okay, so it contains all the information, all there is about that function, and the one on the left, that is only your path. That is the road over there. This is the road. This is the road, and this is the whole road trip. Okay, so if you know your road trip, the way you plan or you record afterwards, you know where you were at what time, and then you can recover that thing, but not backwards, right? Because you can drive in different ways. Even if you stick with a linear function, meaning that you're driving at a constant speed, still there are different speeds. Okay, so that's the difference between the graph. I think I put the graph wrong. This is the graph, and this is the image. Okay, graph, the image. Okay, so that's how we represent points, lines on the plane. Let me maybe write it up. I don't want to think about, I don't want to say it that way. I want to say that what we have discovered is a linear function. Okay, so definition, a linear function from R2, R2 is that. So f of t is equal to p plus tv, where p and v are vectors in R2. Okay, so one point, one vector works out the same way. So there, you can always replace p with a vector, and the vector algebra still works out. That's the vector algebra that we have been doing. We're only doing addition of vectors, so a little bit of an alternative way of looking at it is when the point you can add vectors to points, producing new points. But since we're doing vector algebra, let's say everything is just a vector. Okay, so that is a linear function. As you can see, So just like in dimension 1, linear function is determined by. Oh, I'm sorry, that's not a linear function. This is. Okay, so that's the difference between the thinking about vectors in calculus as well as before, and the way about linearity, and the way we think about linearity in linear algebra. So in linear algebra, that constant is not what makes it not linear, not non-linear, but only this is the linear part. So linear part. So we'll figure out what is the difference later when we have more and more examples. At this point, what is the difference? Not a big difference. What is the importance of p? It only gives you the initial point. So when there is no p, it means that p is equal to 0. It means that your path goes through the origin. That's the only difference. So we are making things simpler, but not also without really losing a lot. So like this. So this is, if this is x and this is y, this is the image of f. You can write it in this way of, once again, following the idea of vector notation. X is equal to f of t. X in Rn, I'm sorry, R2, and t in R. So as you can see, the function is, well, let me use the notation that I have used. So a function f is from R to R2. One-dimensional numerical domain and vector codomain, two-dimensional codomain. Okay, as you can see, it is the similarity with the linear functions in one dimension is determined by one single parameter. One single parameter in what sense? So once again, we had back to one-dimensional case. I would use then lowercase letters. I would write it, so dimension 1, x is equal to f of t. Okay, and then specifically for a linear function, it will be, say, well, how about t times v? Okay, so dimension 1, so t is still a real number, but then our two-dimensional, or n-dimensional rather, output of the function becomes a number. So everything is about number. It's about multiplication of one number by the other, and that's the whole analogy. So this is the input, and v is the output. Not the output. It is the parameter, the single parameter of f. So in other words, for every v, there is a linear function, right? So I could pick 1, 2, 3, or 0. Each of them will give me a linear function, what we discussed early on in this class. Okay. Okay, so that gives us kind of a classification of all functions in dimension 1. In dimension 2, slightly more complicated, but really not that different. So let me write that out again. Capitalizing things that are vectors, and then scalar multiplication of vectors. And but the rest is the same. The rest is the same. Their input is the same, t, but that parameter that determines f f capital, is this time a vector. So of the function. So once again, f lowercase give you a function, and every linear function is determined by v lowercase. Then we move on, and then we say that for every linear function there is a vector v that determines it. On the other hand, whatever v is, it determines a linear function. Okay, so all the linear functions are right here. Like I said, the parameter, however, is not a number anymore. So what is it? We know it is the direction of the vector, of direction of our motion. But we can be more specific once we remember what the meaning of v in dimension 1. What's the meaning of v in dimension 1? No, that's the language we use for dimension 2. For dimension 1. What's the meaning of v? What? No. It's a number. What is that number? What does it stand for? I guess the confusing part is that I'm using the wrong letter. If I use the right letter, you will recognize right away. What if I use the letter M? No. Slope. Yes. Yeah, it is the slope. Usually you have mx, and then you know that m is the slope. But letters, since we are moving into high dimensions, the letters look slightly different just to have this pattern continue on. So anyway, it is the slope indeed of the line, that line that you see over there, rise of the run. Well, not that line. I'm sorry. This line. So t and x. I have my straight line, and my this is the run, and this is the rise, and then the slope is rise of the run. Okay, so so what then, based on this, what is the meaning of v capital as the vector? And the answer is already, we know what it is. It is once again the direction of the vector, and that is the best way to understand it. But we still want to be able to trace the idea back to the one-dimensional case, and the answer is it is two slopes. Okay, the vector has two components, and each of them is a certain slope. Okay, so you can see it in this picture. This picture. So if we take the graph. Well, actually, probably you don't have to necessarily visualize it. Suppose, let me show what I'm talking about here. Suppose v is 2, 3. Okay, it is always a good idea just to break it. Well, the big idea that we're pursuing is that vector notation is very good, and vector algebra is very good, and putting everything compactly as we have is a very good idea. But once in a while we have to go back and actually break it into components just to make sure that we're still on the solid ground and we're just not lost entirely within notation. So let me do that. So if v is equal to 2, 3, x is equal to xy, and well, t is t. Okay, so then what I'm looking at is in fact this. Let me write it in the column form. So x is xy, t is just a number, and v is, say, 2, 3. Okay, so that is I specified v as a specific vector, and x I just named the two components of that vector, x lowercase, y lowercase. So then my equation becomes this. Once again, going from abstract to concrete, back to specifically two-dimensional situation, just to make sure that we are okay, not moving too fast. And so now we can, that is still a vector notation, but I could break it and go into even more elementary. So, and do it, remember, component-wise. X is equal to what? That's right. And y is equal to, what? That's not a 2. And y is, what? T times 3. sometimes put a brace here to indicate that they come together. Okay. Here, 2 is, what is the meaning of 2? Is what? Well, that's not what I meant. Think about what we're looking at x equal 2t as, okay, let me move. It is, in fact, the slope, indeed. So t here and 2t there is the slope. The slope of the line x equal to t, and 3 is also the slope, but the other line. Both of them have the same input variable, but we don't care. If we look at these two separately, one and then the other, and we could, right? One equation of a straight line, the other equation of the straight line, and it's clearly that 2 is the slope of the one, 3 is the slope of the other. Where do we see them? Where do we see them on our graph? Suppose that at the top, suppose that's what we're talking about, and our direction vector was 2, 3. Well, it's not. Well, let me plot it. Okay, let me correct myself here. Okay, so if my direction vector is 2, 3, looking roughly like this, so this is 2, and this is 3, and this is my line. So this is my line as it is represented by our vector equation, x capital is equal to t times v capital. Okay, but now I want to split it into components separately, and I did. I have them over there. So in the original, the meaning of 2, 3 is at the top. It is the direction of vector 2 and 3 that 2 this way, 3 that way. But now we're talking about slopes. So where do we see these? How can we actually visualize these two slopes? Well, I mean, two functions. Once again, think of them as separate, entirely separately, and just plot them. Okay, so that's how you visualize it. One, the other. The x's are carefully marked, t and x, t and y. Okay, so one will be slope 3, and the other one is slope 2. Okay, so the question is, what does it have to do with the original at the top? Do you see slope 2 in the original picture? Well, the answer, what?
Where's the original picture?
The original on the left, top left. The original meaning vector formula. 2, 3 is the direction vector. It is the line is on the xy plane that represented by that function, and then we decide to go back, and then we ended up with two functions and two slopes. And where is those two slopes in the original picture?
Since those are lines, is that where they intersect?
Well, that's a good question. Do they intersect?
Because there's x equals 2.
No, they don't intersect. Look at the x's.
Oh, okay.
The x's don't match, so you cannot overlap these two because the vertical axis is one y and the other on x. So they're not like this. What's the relation between these two planes? Tx plane and ty plane. What's the relation?
T.
Right. So can you imagine what they look like together?
They look like the vector version, right?
No, I mean just the planes. What do the plane, tx plane and ty plane, how do you put them together?
3 dimensions?
Yeah, like this. They have tx's in common. That's where it is. So this is my x and this is my y. The vertical is y. The horizontal is x. But they have tx's together. Okay. So these are the two planes that are available. But really, then the question is where do on that plane we put all of these three lines, one on tx plane, the other one on ty plane, and the third one, the original, on xy plane. So we have three lines, seemingly three lines, but really let me try to put these together. So this is how I'm going to be doing it. I'll put x here, I'll put y there, I'll put t horizontally, of course. Okay, then I take these three lines that I just constructed. So for the y-axis, on the ty-axis, this is my ty-axis. That's the same picture, right? Slope 3. Okay, then I have slope 2. That's a bit complicated, but it is on tx-axis. Do you see which way it's going to go? The purple picture with slope 2 on tx plane. Which way?
Coming out towards us.
Towards us, right, like this. Okay, slope 2. Slope 2 meaning in this sense. This is the slope within the tx plane. This one was within ty plane. Okay, so for each 1 unit, if this is 1 unit, then vertically we went 3 here, and horizontally in the x direction 2 there. Okay, fair enough? Right? The two slopes visible right there on within those planes. As we constructed, we just put the two planes together, two coordinate planes, tx plane, ty plane put together, including the pictures. Okay, so I did not try to do this. I did it in three-dimensional space. So now the third line over there, the third line. Okay, so it lives in the third plane, xy plane. Okay, so I don't have, let me put some nice color here. How about red? So it's going like this, maybe. So what's the relation between the three lines? No, yes, but we don't really care about that. There's a more profound relation. Neither one is the right one. None of the three is the right one. They come from the same source. What is that source? So 3 lines, you cannot derive one from the other, right? So they lie in 3 different planes, so you don't know which one. You cannot discard one and then say I'm okay. You need all 3. But in reality, these 3 are nothing but, that's the picture over here. I'll keep coming back to this picture. Yeah, this is the picture. The graph of the function it goes like that in the 3-dimensional space. It's a straight line in the 3-dimensional space, and those lines that we are facing here are nothing but shadows, projections of that line. Okay, so 3 planes, 2 vertical, 1 horizontal. The line is sticking out at us. Okay, and then you can have 3 projections, shadows, on these 3 planes, depending on where you put your spotlight. If you put spotlight at the t-axis, you'll have the red shadow on that wall. Or you put it from us, then it will be orange. And if that light comes from above, the shadow will be on the tx plane, and that's the purple one. So we use not interchangeably, but we have to decide which one we prefer, either these 2 or the one original, and the original meaning on the xy plane. Which one represents things better? I think the one on the xy plane is better representing things. But really, in the back of our minds, we should remember that there is really one line in the 3-dimensional space, and that is the line, the graph, that contains everything, and these are nothing but shadows. Okay, so it's an issue of visualization on one hand. On the other hand, it is really there is some interconnection of things. How these things interconnected? It is our function of one variable, f capital, is actually made of 2 functions of the same variable t. Okay, And so, so you certainly can continue on, and instead of having two functions like that, you can have three functions. And then the vector will be not two-dimensional, but three-dimensional vector. And then you see the problem. So if my vector v is in fact three-dimensional, what happens to the whole construction here? Suppose v is equal to 2, 3, 1, three-dimensional vector. What changes? There will be z here, right? Equal to 1 times t. Okay? And 1 is the slope. Okay, so we're just trying to make it three-dimensional. What happens? What happens to those pictures on the right? They will be shadowed, but of what? So first of all, how many pictures? Right now I have one picture, I have two pictures for x, a picture for y. There will be a picture for z, right? So z, there will be, I'm going to need three axes, x, y, z, and then I ask myself, where do I put what? T. There is no place for t. And we are in trouble, really, because we cannot visualize that anymore, because we need 4 dimensions. Okay, so it's still, you can still think about shadows and 4-dimensional vector, and then it casts its shadow on the planes, tx plane, ty plane, tz plane, fine, but then there is no, our 3-dimensional space will, even then, our 3-dimensional space will only give us only a slice of that 4-dimensional space, and we will be seeing only part of it at every time. So for as long as we're still, our function is from R1 to R, the graph is still 3-dimensional. We can visualize it completely. I didn't do it, but you can imagine that it's roughly going maybe this way. Okay, and then you can, if you want to go back to 2-dimensional, you can plot x coordinate, y coordinate separately, or ignore t and plot it on the xy plane, and you're fine for the time being. But then, like I said, you cannot visualize that in any dimension higher than 2, because we run out of dimensions in our space. Okay, so that's why the course is called linear algebra, not linear geometry, or linear visualization, because ultimately we have to go back to algebra period, and all of those little pictures that we are able to make will not be available anymore. So then this formula becomes crucial in high dimensions. So we could still split it into multiple functions, as I did here, x, y, or x, y, and z, and then you can have 4 or 5, as many as you like. But visualizations are out of the window, and so we have to actually think about the formula as is, nothing but vectors, and you don't have probably a good idea not to even think too hard about what the dimension is. So these might be n-dimensional. X is n-dimensional, and then something is happening in the n-dimensional space. T is 1-dimensional, so that's good news. It's just a scalar, and so other than that, we are not we cannot visualize anything. But we're still able to at least to catch some of the of that if we just do one component function at a time. So that's the way to describe them. Let me write it. So x is equal to f of t equal to t times v is a linear function. So suppose v is equal to v1 vn. So now we're talking about n-dimensional space. X and v are n-dimensional. Okay. Are you familiar with this symbol? Is a member of, yes, is a member of or belongs to, just for abbreviation sake. So they are n-dimensional, and suppose my vector is v1, vn, okay, and then I could write out just the way I did, I can write out this equation in the form of columns. So I'll have x1, x2, xn. That is my x. And then I continue writing. I have my t, constant, scalar. And I have here my vector v1, v2, vn. Okay, and then what I do is I split it into component functions. Components of x and component of v match, and they create component functions of f capital. So once again, f capital, or anything capital, stands for vectors, and so that's a vector-valued function. But we could split it into n scalar-valued functions. So in other words, x1 is equal to tv1, x2 is tv2, xn is tvn. Okay, so these are the component functions, n of them. Yeah, one from each dimension. So these are elementary functions in the sense that they are scalar functions from that you've seen so many times. So each of them can be plotted on the say tx sub 1 plane. It will be a linear function, and the slope is, I'm doing only one, the slope is v1. Okay, so if you can build or visualize n of those, then you have a picture of the whole thing, but not really very productive. So when you have two, you kind of can put together. So when you see two, or especially three shadows of something, you can actually figure out what that thing looks like. In fact, that is the way they do MRIs. They scan you, and that's how they create three-dimensional picture. They scan it from different directions and then put these computations together in order to create to know where everything is. So that's roughly what we saw here. Well, imagine that that purple line is our, it is three-dimensional, okay? But we only have available the red, the orange, and the purple lines. We could figure out what the purple, okay, I'm running out of colors here. The purple that faces me, that is, okay, let's call it violet, the one that goes up. Okay, so we do not know the violet curve. We can reconstruct it from the rest of the other three. The red one, the orange one, and the purple one, through a fairly simple algebra. Okay, after all, we know the coordinates, and that's how they do three-dimensional imaging when whether it is a person for medical purposes, or they do scanning of the underground for oil or something. That's what's happening there. Okay, so that is the basic idea. Let me do something that just I'm not positive that we are past that. So we're talking about functions, and with the input still a number. So I want to do a visualization of that with Excel. Okay, so I'm going to just visualize a straight line the way we have constructed it. So there will be a column for x's, for t's, t here, and then and here these two columns will be devoted to x and y. X and y, the output. Okay, so once again, this is the input, and these two are outputs. No, well, you can think of it as outputs or one vector output. Okay, in fact, let me do it this way. Where's that thing? Oh, here it is. Okay, let me put it this way. Okay, so x and y are not apart, they're together. Okay, so I'll put t values of t here of my choice. Let me put h, the increment of t at say 0.2. Okay, and here I will start at say 0, and then I will increment it by h, 0.2. So it will be equal to this plus h, which is row 2, column 1. Okay, so I don't remember if did I show you how this is done, how Excel does it. So it does references. R whatever follows R stands for row, C stands for column. So R2 R2C1 means second column, second row, first column. Okay, I'm making reference to that value for one single purpose, is to building the input values. Okay, so so that's R minus 1C refers to the previous row and same column. Okay, so that's the how Excel operates. Okay, so we might talk more about that. Okay, so I have a bunch of t's, and now I will be constructing x's and y's. Okay, by what? Well, how about I put a vector here, a v. Let's put a vector v here. So v is how about 2 and 3, 2 and 3, and okay. So that is my vector, a vector v at the top. I will be referring to these numbers in my column. So x is 2 is the x component of v, and 3 is the y component of v. Okay, so I will be referring to the value of t. Naturally, it's a function, right? So the input of variables are here in this column. And then, okay, so let's just do it. So I will be simply multiplying t by 2. So it will be R1C. Okay, so I will be referring to the first row, and I will be multiplying it by this number. Okay, so in other words, by t. So t is multiplied by 2. Okay, and then that way I get a bunch of x's. I fill down. Okay, and now I'm doing the same with y. So I will be referring to row, well, once again, so it will be row 1, same column. Okay, multiplied by t over here. Okay, naturally the output is 0. I have a bunch of x's and y's. Let me make clear that we're talking about vectors again. So just putting those things on left and right. Okay, so you see a bunch of vectors, right? X's, xy's, and their numbers. So if you look, read horizontally, you will see input t number, then followed by vector with 2 components. Okay, so and now we could that's what Excel gives you, an easy way to plot it. So I just I plot scatter plot. Okay, scatter plot, and well, how about this one? Okay, so that's all there is. So as you can see, once again, the output is two-dimensional. You can see the 2 columns highlighted, the x's and y's, and the relation between x and y is what is plotted. So those little edges are added by Excel. That's not a part of the data. Excel only takes the numbers that we give it and then plots them, and it connected by the curve into or one at a time, and that's what creates the line. But it's really just a bunch of points, these points that we have computed. And as you can see, the t-axis is missing. The t-values are missing. These are only x's and y's. And we do discover that the answer is a straight line. Okay. However, certainly you could look at it. I could vary. I could start, for example, t equal to -3, for example. Doesn't make any difference. As you can see, it recomputes. It's the same line, just starting at a different location. I could stretch it beyond if I make my step larger, say 2. As you can see, it's the same line, but the increment becomes higher. I could vary the slope. Say I put a 5 here. Okay, so that's it. Unfortunately, Excel does not understand proportions, so if I change the dimensions, it automatically resizes it. And so as you can see, the slope should be 5/3, but it is, you can't even tell because different x's and y's are different. Well, anyway, so this is how, that's the meaning of a function of one variable, real valued variable, the chi column. And output, there are two outputs. It's as if you have two separate functions, one for x and one for y, just what we just discussed a minute ago. But the big point to be made here is that we combine those x and y in one. So then, while this is the input, this is its output, the vector of two components. And then, well, the way you plot it is really up to you. And you can imagine that beyond this, it will be very hard to, even three-dimensional vectors, I can easily do computations. I could have as many columns as I like. The number of columns gives you, it is simply the dimension, it is the dimension of our output. So instead of having this, how easy it would be, just insert column, okay, and I have z. I have z here, and I can continue on and say I have here maybe -2. Okay, so that's the direction vector. Now along the z direction is -2. Okay, and then I could do this maybe, let's see. Okay, what is the value here? I'm supposed to be referring to this. Oh, come on. I'm supposed to be referring to this. I'm referring to time, so over here. Okay, as you can see, these are the values of z. I created it from nothing very quickly. The problem is that Excel cannot plot three-dimensional, and certainly beyond that, it cannot plot anything four-dimensional as well. So that's the challenge, and that would have to happen in your head entirely. On the other hand, you can still do what we just did a minute ago. This is a scatter plot for xy, right? What else can I do? So this is xy. Come on. So this is xy, okay. What else can I do with this data? In the same, what? I could do the zy. So exact same thing, or yz. I highlight these two columns, and then a scatter plot is scatter plot of this, once again with what Excel gives me. Okay, so as you can see, we have two. So just like what that analysis we did, except now, so this is yz, except now Excel does it for us. So yz, well, there's one more that we can do. We can also do zx, zx, yes. So xy, yz, xz, and there will be three lines seemingly unrelated to each other. They are unrelated to each other. But together, those are no more than shadows of our of the actual curve, the curve that we cannot, Excel cannot plot. In three dimensions, we could still imagine, at least imagine, or if we had like holographic pen or something, one day we might have, you can actually plot something in space. So as long as it's three-dimensional, we can still do it. But if we go anywhere beyond that, then we are in trouble. So let me do the third one. So I'll highlight x's, and I'll highlight z's. Okay, and so once again, I insert scatter plot. Okay, so that's the third. So this one is xc. Okay, so how you imagine them, how you can imagine what that, well, can you? What does the graph look like? So these are the three shadows of the graph. What does the graph look like in space? Which way does it go? So imagine the three-dimensional space of the three axes, and it starts at the origin. Which way does it go? Okay, so think about, say, so it's hard to visualize on a piece of, on a paper or on the board. So imagine, let's use the walls and the floor. Okay, so suppose that corner over there is our origin. X-axis goes along the floor towards me. That's the x-axis. Where I'm seeing this is the x-axis. That's the y-axis going horizontally in that direction, towards the door, and the z-axis is vertical naturally, right? That way, and then there are three planes, and they cut the space into how many parts? No. How many rooms? How many rooms adjacent to that point? Our room next door, then there are in a way 2 rooms over there, and then the same thing below. So it's actually 8. That's why they call it octants. 8 adjacent pieces of the space. So you cut it this way, that way, and this way, and you cut the space into 8 pieces. And what you can ask yourself is which way, under these conditions, to which way we're going to go. So okay, so just look at it. X is, what's happening to X? It is, well, let me put 0 here in order to make our life easier. I'll start time at 0. Okay, so X is growing, Y is growing, and Z is decreasing. Okay, so X is growing, so we are moving along this axis towards me. Moving along the Y-axis also in that direction. But the Z direction is down. So in other words, we are moving from that location over there, we're moving into the room right below us. Like this, right? Like this. Yeah.
Yeah.
Right.
Can't really see 'cause I'm here.
Yeah. So like this, if you can see in 3 dimensions. So it's points down and in towards us, but down. Okay, so that's as you can see, that's the challenge, to figure out actually what's happening based on nothing but this kind of data. Or you just look at the vector 5, 3, -2. 5, 3, -2. Okay, it's going down. Okay, so I'll assign homework later today.